Okay, so chapter
So
3 is all about
chapter 3 is all
derivatives,
about
and I had some
and
remarks in the
remarks
discussion section just about the link
about
between
the link
limits and derivatives.
between
There is a limit
derivatives.
definition for the
There's a
derivative
limit
that you saw in
that we
2.6,
saw in
and
2.6,
it's
and
interesting.
it's
It
interesting.
links these two ideas, but it's not the
But it's
tool that
not
we
the
ever
tool that
use
we
once we
ever
figured out
use
shortcuts
once
for
we
how to
figured out
find derivatives. So
shortcuts
one way that
for
you
how
can
to
think about
find
chapter
derivatives. So one
3
way that you can think of
is, all right,
three
at the end of chapter 2, we were
is, all
introduced
right,
to this
the
idea of an
impact
instantaneous
we
rate of
were
change
introduced to this
and
idea
given
of
a
an
pretty complicated way to go about
given a
finding
pretty
it.
complicated way about
What we can do
finding
now with some
what we can
shortcuts
do
and some rules
now
of
with some
derivatives
shortcuts and
is
rules
speed
of
that
derivatives
process up and make it a
is
lot
speed
more
that process
efficient.
up and make it a
I
lot
wanted to look
more
at
efficient. I want to look at a
few easy derivatives to take
easy
and
derivatives
just
to
make sure
take,
that we're on the same page with
make
notation.
page with
So just to
So
begin with here, and apologies in advance if I move
begin
outside of
here.
the screen
Apologies
range
if I
here,
move out of the screen
or
range
it's a little
here,
jerky. I'm
or
using
it's
my
a little
iPhone
jerky. I'm
as
using
a document camera right now.
right now.
But
But
if we have f of x
we
is a
have f
function
of
that we're
x as
looking
a
at,
function we're looking at.
then there's a variety of different notations that we might use to talk about the derivative of f. Most commonly, we might see that written as f prime of x. And right now, I'm just going to call that the derivative of x. As we get deeper into the chapter, you'll see that that's not actually the end of the story. We can be a little bit more specific about exactly what that represents. But f of x is some function that we're looking at. Could model anything. Could model population. Could model money in bank account. Who knows what? F prime of x is the derivative. It's the instantaneous rate of change in that function for some value of x. And f prime of x is itself a function. It's a different function from f, but it tells us something very important about the original function. So f prime of x is the first derivative of f. And then the last part here is with respect to x. So it's kind of like its long title here. I'll just explain what those two things mean. The first derivative, meaning it's the first rate of change. And section, I think it's 3.5, we'll see higher order derivatives, second derivatives, and third derivatives, and so on. They're not that hard to work with, but if we're just looking at the rate of change function, it's going to be a first derivative. Quick example, if we have a position function in physics, then its first derivative is velocity. There are other derivatives, like the second derivative is acceleration, the third derivative is jerk, and so on. But primarily, at the beginning of the chapter, we'll just be working with first derivatives. So first derivative of the function f, and this last part here with respect to x, what that means is x is the independent variable, x is changing a small amount, and the derivative is going to tell us how much f of x, the y value, changes. So just a little bit of background here. Some other things that you might see, if you have a function like y equals some function of x, you might also see the derivative this way, dy dx. That means the exact same thing. So dy dx and f prime of x and d dx of f of x. These are all slightly different notations that all mean the same thing. They all mean the first derivative of f with respect to x. So you'll see in WebAssign different notations, but they're all asking the same thing here. Okay, so how do we find these things? Well, the limit definition of the derivative, you need to know it. You need to recognize it. On the quiz this weekend, you're going to be asked to do maybe one problem where you go through the process of evaluating this limit, but it's not a major emphasis as we move forward in the course. So here's the limit definition. The limit as h approaches 0 of this difference quotient. And the difference quotient is really just a slope calculation between 2 points. So in the numerator, I have a change in y, and then in the denominator, I'm going to write it and then erase it because I got a dry erase board here. So, oh, sorry, I have one little typo here. It's x plus h. So here's some x value, and then here's another x value. So here's like my delta y, and here's my delta x. And if I take x plus h and I subtract x to find that difference horizontally between these 2 points, algebraically that's just going to end up being h. All right, so this is the limit definition of the derivative, so of f prime of x. And graphically, what this means is take 2 points on the curve and calculate the slope of the line connecting those 2 points. That's what we call a secant line, and it gives us an average rate of change between those 2 points. It's not yet a derivative unless we move those 2 points infinitely close to each other, at which point we have an instantaneous rate of change or the derivative of the function. That's what that limit part represents. H is the horizontal distance between these 2 points, and I'll just illustrate that over here in a small diagram. So here's some function f equals f of x. Here is some point x, and then if we move horizontally by h units, we'll end up at the x-coordinate x plus h. And then the height of the function of those 2 points will be f of x. And then the height of the other point will be f of x plus h. And so then the change in y is f of x plus h minus f of x. And the change in the x direction would be x plus h minus x, giving us h. So it's really just a slope calculation where we're now squeezing these 2 points as close together as we can. That value of h is going to diminish down as close to 0 as we can make it. So this is the formal definition of the derivative, but as I mentioned, it's not really how we calculate derivatives. We can prove all of these properties using limits, but it's not really an emphasis of this course to do a whole bunch of proofs as to why things are true. If you're curious, Khan Academy has some really good videos that will show a full proof of any of these properties if you're curious about it. So here's some facts about derivatives that will be helpful in chapter 3. The first is that the derivative of any constant is 0. And notice how I'm going to write that. I'm going to write d dx. Okay, so we can think of that as the verb form of taking a derivative. Here we have the derivative, dy dx, f prime of x, and d dx of f of x. These are all referred to the derivative. When you see this notation here, it's telling you to take the derivative of what comes next. So I'm going to take the derivative of the function y equals some constant. Okay, so it's not a variable just because it's a letter, it's a constant, it's some number. It's like the derivative of 5, or the derivative of 2, or the derivative of negative 3. Well, if you think about what that function would look like, if y just equals some number, so like y equals 5, for example, y equals 5 is a horizontal line, right? And one of the things that we know about the derivative is it measures the steepness of the curve. Well, any horizontal line has slope 0. And so any tangent to that curve that we could draw would also have slope 0. And so we have this first result that the derivative of any constant is just 0. Okay, so what else do we have? So we have some other just general properties of derivatives. And these come directly from properties of limits. So here's another one. So we're going to take the derivative of some number times a function. Right, so and I'll do a specific example here. So like this is 5x squared. So the function is f of x equals x squared, and now we're taking that and multiplying it by 5. How does that affect the derivative? Well, it affects it in a pretty predictable way. It's just going to be the derivative of the original function f times that constant. I'm going to erase stuff down here for example. So on Thursday of last week, I did one limit definition of the derivative problem, and what I showed was that if f of x equals x squared, then f prime of x equals 2x. So even if you didn't tune in to that particular session, this is something that I know, and I hope you'll trust me on. So this is a known derivative. What the second rule of derivatives allows us to do is to expand our knowledge to new functions. So if we know that the derivative of x squared is 2x, that means that the derivative of 5x squared is going to be 5 times the derivative of x squared, and that's something that we already know. So it'll be 5 times the derivative of x squared, and we know that the derivative of x squared is 2x. So 5 times 2x is 10x. All right, and again, this is a shortcut. It's something that you might suspect to be true, but we've actually gone and proven that this works for all functions, and we've done that using properties of limits. Keep listing these, get rid of that exit. Okay, if we need to take the derivative of a couple functions being added or subtracted. So here's one function, and then we're either going to add or subtract some other function. Okay, well, if we're adding the two functions, we are allowed to just take the derivative of the first function and add it to the derivative of the second function. If we're subtracting them originally, we will take the two derivatives independently and subtract them. I should just note here, when I write that plus or minus, you might recognize that from like the quadratic formula. It actually means something slightly different here. It means that this property works for both addition and subtraction. So if we're adding the functions originally, we'll add over here. And if we're subtracting originally, we'll subtract over here. Both of those things work. Okay, this is the big one in terms of making your life easier, taking derivatives. So this allows us to take derivatives of powers of x. So any power of x, so x to some power n. So for example, x squared or x to the 10th. And here's the shortcut. By the way, if you ask people 10 years after they've taken calculus, what do they remember? This is often the one thing that they remember most, is this rule, this shortcut for taking derivatives. The shortcut for taking derivatives of powers of x is we're going to take that power and bring it out in front as a coefficient. So we're going to multiply the whole thing by n, and then we're going to drop down that power by 1. So if the original function was f of x equals x to the n, then the derivative will be n times x to the n minus 1. And that's worth a couple examples just to make sure that that sinks in here. So if we want to take the derivative of x cubed, so in this case, n would be 3. So looking at the structure of the derivative here, what happens to that original power is it comes out in front as a coefficient. So we're going to have 3 something. And then the power of x drops down from n to n minus 1. So originally, the power was 3. So I dropped that down by 1. And now I have x squared. So there's my derivative of x cubed. And that's really nice because the alternative is to expand a big polynomial and do all this collecting like terms and canceling. And it's really arduous. It doesn't really illuminate what's going on. So these shortcuts are going to allow us to deal with a whole collection of more complex functions. And then the cool thing is that we can use these rules together. So for example, just up to 3 now maybe. Let's say I want to take the derivative of a polynomial. So maybe I have 4x cubed minus 5x squared plus 3. So these 4 rules allow me to do several things, and I'll show all the steps. I don't expect that when you're solving a problem, you're going to necessarily show all these steps. But you know, the third property here says I'm allowed to add or subtract derivatives just in the same way that the original function was added or subtracted. That allows me to take this problem and actually break it into 3 separate derivatives. So the derivative of 4x cubed minus 5x squared plus 3 is going to be the same as the derivative of 4x cubed minus the derivative of 5x squared plus the derivative of 3. And so I've taken a complicated looking function, just like broken it into 3 much easier functions for me to deal with. Okay, well I can actually go even further here. I have this constant multiple rule, rule number 2, that says, okay, if I have something times a function, I can actually just factor that out in front and find the derivative of just the powers of x by itself, for example. So I could go even further and say, all right, well, if I want to make this easier, I could factor that 4 out and say, okay, well, 4 times the derivative of x cubed minus 5 times the derivative of x squared plus the derivative of 3. And now we have a really easy problem. We can just use powers of x, right? Rule number 4 and rule number 1 to complete the problem here. Well, we already figured out the derivative of x cubed is 3x squared. So we just need to multiply that by 4. So it gives us 12x squared. And then minus 5 times the derivative of x squared. So we also did that, and then the derivative of x squared is 2x. So minus 10x And finally, the derivative of 3, that's a constant. That's our first rule here. So the derivative of 3 is 0. And so here is my final answer. And that's the derivative of our original polynomial here. So let me just pause here and see if there's questions about any of this stuff so far. Whoops. There we go. Good. Awesome. So, we'll take care of this. All right, we'll leave it like that with the cable dangling. Okay. All right, so one thing I want you to notice in this collection of rules is we're allowed to add and subtract the derivatives, but we're not allowed to multiply and divide them. So in fact, it's not the case that the derivative of two functions multiplied together is the derivative of the first times the derivative of the second. Sections 3.2, 3.3, and 3.4, if I remember right, all have to do with some additional rules for taking derivatives. The good news is they're short sections. Each one is not very long, and each one gives you a new rule, a new tool, a new formula. And these are definitely required knowledge here. Let's see. So this next rule has a name. It's called the product rule. And it tells us how to take the derivative of a product, so two functions being multiplied together. So if you want to take the derivative of f of x times g of x. Okay, so there's a little bit of a formula involved here. Again, I'm not going to go through a proof in this session here, but there's lots of proofs out there if you're curious. Really, what I want to emphasize is the result here, because the result's going to allow us to find derivatives for a whole class of functions that we couldn't do otherwise. So here's how we do it. We take the derivative of the first function, so the derivative of f, and multiply it by the original function g. And then we're going to add that to f times the derivative of g. Okay, so we have the derivative of the first times the second, and then the derivative of the second times the first. Add those two things together, and that's our product rule. That tells us how to take the derivative of two things multiplied together. So here's an example. Let's say we had to take the derivative of x squared times the square root of x. We may actually come back to this problem later because there's a second shortcut that can actually eliminate the product rule. But this is a nice example here. So I have two functions here. I'm just going to label them so that they match my formula up there. I have f and g. So two functions being multiplied. So now I need to use the product rule. And what the product rule says is the answer is going to be the derivative of f, so d dx of x squared times g, so times the square root of x. And then add that to x squared times d dx of the square root of x. Okay, so I can do one of those. I know the derivative of x squared is just 2x. So I have 2x times the square root of x. And then the second part, I'm going to add f, which is x squared, times the derivative of the square root of x. Now that's actually worth a little sidebar here, because we haven't really learned how to take the derivative of a square root function. But what you might recall from college algebra is that we can rewrite a square root as a fractional power. So the square root of x is the same as x to the 1/2 power. And if we write it as the 1/2 power, the derivative is actually very easy to take. We can use the same rule that we used for x squared and x cubed and any other power of x. So d dx of x to the 1/2. Same idea, we're going to take that 1/2 out in front. and then we're going to decrease the power of x by 1. So if the original power was 1/2, and then we subtract 1, we'll have x to the negative 1/2 as our derivative there. So I'll just transcribe that down here. So 1/2 times x to the negative 1/2. And here's our answer for the derivative. By the way, in WebAssign, it shouldn't be bothered by the fact that this is unsimplified. We don't really want to waste your time or our time testing you on simplifying powers of x. You can write it exactly where it is here. It is possible to sometimes combine like terms and things like that, but don't worry too much about that. And so this product rule has to be used anytime we're trying to take the derivative of two functions multiplied together. Now I want to revisit this problem. I used it to just illustrate how the product rule works. But there's actually an easier way to do it, and it's great. I don't know if you guys noticed, one of the things I posted in the discussion forum was this open question: when can we avoid using derivative rules? Well, this is one of those cases. If we use a little bit of algebra at the beginning, we can make the calculus work easier. So it's true that the square root of x is just the same as x to the 1/2 power. So really what I'm asking you to do in this problem is take the derivative of x squared times x to the 1/2. Now there's no reason why you can't combine these terms before you take the derivative. And in fact, that'll make our life easier, because if we do that, we'll no longer have a product. So just using properties of exponents, if I take x squared and I multiply by x to the 1/2, I'm allowed to add those exponents there. So 2 is 4/2. So if I add 1/2, and if I add 1/2, we have a total of 5/2. So x to 5/2. And now by just doing that simple algebraic step at the beginning, I no longer have to use the product rule because I have a single function here. And so in this case, my derivative would be 5/2. Right, so 5/2 comes out in front, and then the power of x drops down by 1. Or since we're dealing with fractions, I can think of 1 as being 2/2. I'm going to subtract 2/2 from my exponent, leaving me with 3/2. Has the sound gotten better, or is it still echoing?
It's better, yeah. There was a few times where it kind of got bad, and I wasn't sure at first if it was mine computer or yours, but I think it's good.
All right, so I'm going to add the quotient rule, and that might be a good place to stop, just so you don't have a million rules all at once. Take a look at some WebAssign problems. So product rule has to do with products, right? Product just means the answer to a multiplication problem, and the quotient rule has to do with quotients, and quotients are the answers to division problems. So we're going to use this quotient rule in the situation that we have one function divided by another. So here's our quotient rule. Product rule is not so bad. Quotient rule is a little bit trickier. So in general, we're talking about a situation where we have a function f divided by, sorry, my x's are looking at t's there, divided by function g. And here's the formula. It's a little bit messy here. So g of x times f prime of x minus f of x times g prime of x. And all of that is over g of x squared. That's quite the formula. It's in your books. It's in the digital textbook as well. It is something that you'll need to know. You'll need to memorize. If this were an in-person class, like your exam, not provide that formula for you. I'll tell you how I remember it. In the original fraction here, f of x is like the higher function, and g of x is the lower function that's just in the fraction there. So I've heard this described as low d high Right, so that's the g times f prime. So lower function times the derivative of the higher function, low d high, minus high d low, all over low squared. In the in-person version of this class, we let people have a note card for the exams, and what I found most people write rather than f and g is they write low d high minus high d low over low squared for this formula. I've been doing calculus for 20 years, and that's still how I remember it. So I'm going to erase some of the stuff up here and do an example of a quotient rule problem, and then maybe just a little bit of commentary on when we can avoid using these rules if possible. So let's do this. So let's let f of x equal x squared over 2x minus 1. And let's do the following. Let's find the slope of the tangent line. The slope of the tangent line to y equals x at, let's say x equals 1. Okay, so you'll see problems like this, and they might throw you for a loop at first. Remember that the derivative is three things. The derivative is the instantaneous rate of change. So if you're ever asked about the instantaneous rate of change, that's just code word for take the derivative. Derivative is the limit of that difference quotient. You won't see that as often, but you will see problems where you're asked to either find the slope of the tangent line or actually find the equation for the tangent line. And again, these are all different ways of asking you to take the derivative of a function. Now for this one, we're going to take the derivative, and then we're going to plug in x equals 1. We're actually going to evaluate the derivative at a specific point to find the slope of that specific tangent line. So looking at my function f, I can see that it's a quotient. There's no real way for me to simplify this. I can't like cancel an x in the numerator and the denominator. I can only do that if x is a factor, like everything's being multiplied by x. Here, the 2x has 1 subtracted from it, so there's nothing I can do algebraically. I'm going to have to use the quotient rule here. Now, I'll show you how to do these problems, and I recommend this for all students, especially when we're doing some new type of derivative. The key to these problems is not being brilliant, it's being organized in your thoughts and to figure out, okay, what pieces do we have here? So I'm just going to label this. I'm going to say, all right, well, that's my high function, and then this is my low function. Okay, and I need like low d high minus high d low all over low squared. So, okay, what do I have here? So I have high is x squared, low is 2x minus 1. Okay, well, then what would the derivative of the higher function? What would d high be, or high prime? Well, if the upper function is x squared, then its derivative is 2x. And if the lower function is 2x minus 1, well, the derivative of 2x minus 1, well, let's just think about it piece by piece. The derivative of 2x, that's still a power of x. That's the first power of x. So we can imagine a 1 being multiplied out in front. Well, that doesn't change anything, multiplying by 1. But then the power of x drops down from 1 to 0, and x to the 0 is also 1. And so the derivative of 2x is just 2. Hopefully that makes sense there. It follows the same rule as higher powers of x. In this case, the power of x, even though it's not written as 1. So now I have these four pieces. I have high, low, d high, and d low. All I have to do then is put them into my formula here. I'm going to write it. So what do we say? We say low, d high, minus high, d low, all over low squared. Okay. Well, with those pieces, okay, well, low is 2x minus 1, so 2x minus 1. Careful with the parentheses there, we want the entire function multiplied. So low d high, what's d high? D high is 2x minus high d low, so minus x squared times 2.
all over low squared. So all over 2x minus 1. Again, that whole thing squared. And I'm done.
You don't have to do distribution. You don't have to collect like terms. In fact, please don't. It's a waste of time, and you might make a mistake when you've done calculus correctly all the way up to that point. So quotient rule is a little bit trickier. Again, it's really just keeping track of moving parts. Some people color code it. Some people circle the top and say that's f of x, and the bottom say that's g of x. Do not feel bad about using those organizational tools to keep track where you are in the problem. It's a smart thing to do. And we're going to see problems where we might even have to combine different derivative rules, and just staying organized in your work is perhaps the most important thing of all. So with those two, I wanted to close, or at least open it up for questions on that, with a couple more examples where we can avoid using derivative rules. I already showed one. One was where we had square root of x and x squared, and we got out of doing the product rule just by rewriting the square root of x as x to the 1/2 and using properties of exponents. Here's another one, and I know that there's at least one problem on WebAssign like this, and we also love giving a quiz problem like this. So here's my second example. Let's let, I didn't finish that problem. I apologize. We should have plugged in x equals 1 and gotten an actual value of that one, but it's erased gone into the ether now. Whoops. All right. So let's let our function f of x be the following. X cubed minus 2x squared plus 5x all over x. And we're asked to find f prime of x. Okay. So looking at the function, the first thing we should notice is this is a quotient. It's a degree 3 polynomial divided by a degree 1 polynomial. And so we should immediately be thinking quotient rule. Now, there's a shortcut in this problem, and here's the shortcut. Just like in the previous problem where I used quotient rule, if I can get away with doing a little bit of algebra first, sometimes I can eliminate the need for a derivative rule. And for this particular fraction, one thing I noticed is that all three terms in the numerator have a shared factor of x. I could factor an x out of all three terms, and in fact, simplify f of x, right? Each one of these terms can be divided by the denominator x. And so my function f is really just x squared minus 2x plus 5. Right? Hopefully that makes sense what I just did there. I took each term in the numerator and divided it by x in the denominator. And now the simplified version of my function is way easier to find the derivative of. All I have now is powers of x. Powers of x are about the easiest function there is to differentiate. Okay, well, so if f of x is actually just x squared minus 2x plus 5, well then f prime of x will be 2x, that's the derivative of x squared, minus 2, that's the derivative of negative 2x, and then the derivative of plus 5, that's just 0. Right, so that goes away. My problem is done really quickly and easily, and without the quotient rule. So as long as you can use valid algebra, and I emphasize valid algebra because I know there's students out there who just like to cancel things out, cross out x's everywhere. You gotta make sure that you're doing it correctly. The reason I'm able to do it here, I guess I could have shown a few more steps here, like x cubed minus 2x squared plus 5x. Well, that's the same as x times x squared minus 2x plus 5. Right? And if I have a factor of x in the numerator and a factor of x in the denominator, that's where I can cancel. You can't just cross out x's, but you guys probably know that already. And yet it's a really common error, even way up beyond calculus. So I think those are the main things I wanted to talk about today. I just wanted to try and summarize and synthesize all these derivative rules. You're going to end up with really just one more derivative rule. It's called the chain rule. And it should be pretty straightforward. There's good videos about that. I'll cover that also on Thursday along with implicit differentiation. I think implicit differentiation is probably one of the tougher topics this week. But are there any WebAssign questions that you'd like to look at? Sorry, I got to
I did have a quick question on more just like generic.
Yeah.
Is there like a way when I submit or like if I've incorrectly done it numerous times and then I just like get it wrong, is there a way to be able to see like the answer to that problem, or to see like how they work it out, just so that I actually can learn from like why I couldn't figure that one out?
In WebAssign?
Yeah.
Yeah, I think so. The answer is yes, but they might not let you see that until the assignment has closed.
Okay.
Until the due date. One thing you can definitely do, if you've submitted several answers and you're not getting it, send me a message like your ask your teacher. There's an ask your teacher button built into WebAssign.
Okay.
You can say like, I tried this and it didn't work, or just like, I have no idea what's going on in this. And what I can see on my end, I can see the attempts that you've already made and try and figure out what the issue might be.
Okay. Yeah. Sweet. I will definitely do that then.
Cool. And I guess like on that same note, sorry, switch my video back here.
Yeah.
Okay, on the same note, if you need more attempts, because I know if you get a problem wrong a certain number of times, they'll lock you out of the problem. You can request a manual extension. And if you just put in the comment, like, I want more attempts, I'll give you as many attempts as you want on a problem that you are trying to figure out. I don't know a way to just blanket like up that number, but that's something that people have done in the past as well.
Okay, perfect. I guess maybe one other question, kind of besides the problems. Are you posting the live sessions or like these on D2L, and
Yep,
where are those at?
Yeah, this one will be posted. Last week I had a bunch of problems with video that I now have like a workaround for it. So I looked back at it and there wasn't much useful video. And I looked at it, I'm like, you know what? I don't want someone watching a half-hour video that contains the same thing as Kim's like 5-minute video. So I didn't put the last week's on, but this one will be up. Actually, as soon as we're done, I'll put it up on YouTube and then link it to D2L.
Okay, perfect.
Cool.
Awesome.
All right.
I think that, yeah, I didn't have any more questions. So
great. Well, I'll sign off and stop recording here. Just a reminder that that you guys can also have one-on-one meetings with me for any reason. If you're stuck on a homework assignment, just use that Calendly link and sign up for time, and I will make time to meet. Cool. Thanks, Travis.